Alrighty, hello everyone. This exercise we're working, or this lesson we're working on exercise 8E. But before we move on to that, I just want to scroll back to 8D. Now, last lesson at example 8, I said, as you can see here, it says trail and or path. However, unfortunately, that's not quite right. There is a small condition, and I didn't get it right the first time, but there's my pen. So in the one we did here, when my rubber wants to work. There we go. A to D to C to F to E to B. That did not have repeated edges and did not have repeated vertices. So since it satisfies both criteria, this one is a path. So I'm sorry about that, but please change your notes to path unless you've read the work example in your textbook and actually fix it yourself. But if you didn't, this one is actually a path because it does not have repeated vertices and repeated edges. Just to clarify that, and it's always good to be corrected. There you go. Work example 8. This walk is a path because of no repeated edges and no repeated vertices. So I'm sorry for that. Which also means that this one might be wrong here. What was this? This F to E to B to C to F. So this one has no repeated edges and no repeated vertices except for the start. So this one here is a cycle. So please fix that, and I do apologize for those mistakes. Moving on to 8E. 8E is a special type of trail. It's called an Eulerian trail, and there's another thing called an Eulerian circuit. Okay, what I need you to really remember is this is an Eulerian trail. This is an Eulerian circuit. Now I'm stressing that because when I scroll down, you're going to move to something called a Hamiltonian cycle. And I've missed a screenshot. And a Hamiltonian path. Sorry about that. So just be careful. Hamiltonian cycle. Never write Hamiltonian circuit, and never write Eulerian path or Eulerian cycle. It's Eulerian trail and Eulerian circuit. So on exercise 8E, an Eulerian trail follows every edge of the graph with no repeated edges. An Eulerian trail will exist if the graph is connected and has zero or two vertices have an odd degree. Okay, so what I mean by that is, let's look at this example here. Let's look at degree A. Vertex A, it's got 2 degrees. This one here has 2 degrees. This one has also 2 degrees. And this one has 2 degrees. So they're all even degrees. Okay, so if let's go to Eulerian circuit. I've jumped ahead a little bit. An Eulerian circuit is an Eulerian trail that starts and finishes at the same vertex. An Eulerian circuit will exist if the graph is connected and has vertices that all have even degrees. Okay, so that means, see how this one has all even degrees? And the question is, determine whether the graph has an Eulerian trail, an Eulerian circuit, or both, or neither, and explain why. So this first one will have an Eulerian circuit. And the reason why is, you just write comma, all vertices have even degrees. Okay, so the Eulerian circuit and trail have criteria that need to be satisfied. And then part double I just wants you to create one of them, show it as an example. So I'll go A to D to B to C back to A. So that is an Eulerian circuit, and an Eulerian circuit starts and finishes at the same vertex and has vertices that are all even degrees. Okay. All right, let's look at this next one. This is 2, 2. Don't be lazy. It's good to circle and write like I am here. 3 and 3. All right. So this one is not an Eulerian circuit because there are some odd degree vertices. However, an Eulerian trail has 0 or 2 vertices that are odd. So as you can see here, there's 2 vertices that are odd. So that means this one will have an Eulerian trail. Trail, yes. Okay. Don't use path. It has to be trail. And that the reason being, 2 vertices are odd, rest, or even degrees. Okay. Don't be lazy, just write 2 vertices have odd. Just write 2 vertices are odd. Well, sorry, not odd. 2 vertices have odd degrees, and the rest or even degrees. So something along that line. And then the last one, well, I'll have to do an example. Let's see, let's do it in green. So this one needs to hit every edge, and where is it? No repeated edges. Okay, so I can't repeat the edge, but I can repeat the vertices. So let's go here to here to here, and here, here, here. Now that's a problem. I didn't exactly hit every edge, did I? Let's have a look. Yeah, it follows every edge and does not repeat the edge. So I'll bug it up there. Let's try again. There we go. Rubbed out the green stuff. Let's go back up. I want to see if there's any hints. If there are two odd vertices, the Eulerian trail will start at one of them and finish at the other. So I probably should have read that. So let's try starting at this odd one. Going to here, going to here, going to here, up here, across. Now I'm allowed to repeat vertices, just not allowed edges, and done. Finish. Okay. Let's check this last one. We got 2, we got 3, we got 3, we got 3, we got 3. So this one's going to be obviously neither, because there's only two criteria. The first one being all even degrees, or only 2 odd vertices, or 0 odd vertices. So that one's neither. Pretty straightforward. Alright, let's have a look at these ones here. Is any more after this? Nope, next one's 8F. Alright, so let's see. That's 2, that's 3, that's 3, that's 3, that's 1. So this one will be neither, because 2, yep, 3, yep, 3, 3, 1. So 1, 2, 3, 4. That's 4 odd degrees, so that's neither. That's 2, 1, 2, 3, 4. That's 4. This is 2, 1, 2, 3, 4, 4. So this one will have an Eulerian circuit because all degrees are even. And this one is 2, 1, 1, 2, 3, 4, 1, 2, 3, and 2. So this one will have the Eulerian trail because it's got 2 odd degrees. Okay. All right. And that's it. Thank you very much.